Hey everybody, Dr. White here to talk about section 7.7 on improper integrals. What we're interested in is the area underneath a curve from, say, a number all the way on out to infinity. So for example, think of y equals e to the minus x, just from 0 to infinity. So here's part of its graph, starting at 0 and going on and on and on in the positive x-axis forever. So, e to the minus 0 is a 1, and then the function decreases rather rapidly, leveling off towards the x-axis. What's the total area underneath it? Is it possible that even though it goes off infinitely in a direction, that the total area is finite? This is, in fact, possible. The way we write this area is as the integral from 0 to infinity of e to the minus x dx. We call this thing an improper integral because infinity isn't a proper real number. How might we try to find this area? Well, we could use the idea of a limit to do so. Think about just the area underneath the curve from 0 out to some number, capital R. It could be any positive number you like. That's a totally decent integral that we can find in the usual ways. But then imagine the r going to infinity. So as the r increases, that upper bound gets more and more to the right, and so you pack more and more of the total area that you're interested in into that integral from 0 to r. So why not take the limit as r goes to infinity of the integral from 0 to r? That's the basic approach here. So that leads to this definition for a certain type of improper integral. The integral from some starting value, a real number a, up to infinity of some function f of x. It'll just be the limit as r goes to infinity of the proper integral from a to the real number r of f of x dx. It's also possible to be interested in going out to the left infinitely far. So like the integral from minus infinity to some real number a would just be the limit as r goes down to minus infinity of the integral from r to a. Okay, let's take a look at that initial example, the integral from 0 to infinity e to the minus x dx. So by definition of improper integral, that's this limit. Now we got to go for this definite integral. So we grab the antiderivative of e to the minus x. We have to evaluate between 0 and r by the fundamental theorem of calculus. And when we evaluate, we get this expression here, which we should simplify. E to the minus 0 is e to the 0, which is a 1. Minus minus is a plus, so we got a plus 1 here. And here's a minus e to the minus r. Okay. Now we need to maybe think a little bit about e to the minus r. It may help to write it as 1 over e to the r, and then consider the fact that r is going to infinity in this limit here. Well, we know that e to the r would have to grow very fast as r gets to be a bigger and bigger positive number, so 1 over it is going to go to 0. And so the limit is actually going to be 1 minus 0, which is 1. So the total area underneath this curve going all the way out is finite. In fact, it's just the number 1. Okay, let's just try another example. How about the integral from 2 to infinity of 1 over x squared? Does this converge, and if so, to what? So trying the same thing, take the limit as r goes to infinity of the integral from 2 to r, antiderivative here of x to the negative 2, evaluate from 2 to r. You get this expression. It's good to take a moment to simplify that. The minus 2 to the minus 1 is just a half, and minus r to the minus 1 is a minus 1 over r. Again, we're in a situation as r goes to infinity, this fraction here goes to 0. And so the limit ends up being 1/2 minus 0, which is a half. So this improper integral does converge. It converges to a half. The total area underneath this curve here, 1 over x squared, from 2 to infinity, is just a half. Okay, one more example. How about the area underneath the curve 1 over x from 2 to infinity? So again, trying the definition, and then thinking about the antiderivative of 1 over x, that's log of absolute value of x. Evaluate from 2 to r to get the definite integral. We've got the log of the absolute value of r minus the log of the absolute value of 2. Now 2 is a positive number. R is supposed to be bigger than 2, is to the right of 2, so it's a positive number. Absolute value of a positive number is itself, so we're really just looking for the limit of this expression here as r goes to infinity. And so we have to think about the graph of y equals log of x. So you know that log of 1 is 0, and you know that as x is bigger than 1, the log is positive, and it gets bigger. It gets bigger slowly, but it gets bigger without bound as x goes to infinity. The limit as x goes to infinity of log of x is actually infinity. And so this log of r piece here is going to infinity as r goes to infinity. So the log of r minus 2 is also going to have to go to, log of r minus log of 2 is also going to have to go to infinity. So this improper integral diverges. The area underneath 1 over x from 2 to infinity is actually an infinite area. So what you should think about really is, why is this happening? Why does it converge sometimes? Why does it diverge sometimes with these improper integrals? It really has to do with how fast the function itself heads down to the x-axis. Think about y equals 1 over x. Here's part of its graph. 1 over x does go to 0 as x goes to infinity, but it goes, I would say, too slowly to keep the total area underneath it finite. You take the area from 2 to r and you'll get some finite number. You let r get bigger, you'll get more area. The amount of new area you get for every 1 unit increase in r is less and less and less, but you are packing it on. And it just so happens that 1 over x goes to 0 too slowly to keep what you pack on from making your total area rise without bound. On the other hand, y equals 1 over x squared also goes to 0, but it goes to 0 a lot faster than 1 over x does. And so as you pack on the extra area, increasing r by another unit, another unit, another unit, as you imagine its limit going to infinity, although you do pack on more area with every unit increase in r, the total area that you pack on stays bounded. It's a matter of how fast your function decreases to 0. We can generalize this thinking somewhat for these power functions. This is Theorem 1 in the book called the p integral from a to infinity. So imagine a is just some positive fixed real number, and you're interested in the integral from a to infinity of 1 over x to the p, where p is some constant power. Okay? It turns out that this improper integral converges to a to the 1 minus p over p minus 1 if p is bigger than 1, and it's going to diverge if p is less than or equal to 1. Finite amount of area underneath if p is bigger than 1, infinite amount of area underneath if p is less than or equal to 1. Let's do a little proof of this. So let's look at the integral from a to infinity of x to the minus p dx. And we pull out the definition of improper integral. Then we go for an antiderivative of x to the minus p, and we've got x to the minus p plus a 1 over minus p plus 1. As long as p is not equal to 1, okay? The denominator would be 0, then the power rule for antiderivatives would not apply. So we're going to have to consider that case separately. We'll bracket that and look at it later on. Okay, and we'll evaluate between a and r. And so when we plug in r, we get this, and when we plug in a, we get this. And I think a little bit about these minus p plus 1s. You know, the opposite of minus p plus 1 is p minus 1. And I've got a minus sign here in front of this expression, so I can put that minus in front of the minus p plus 1 and get a p minus 1 on the bottom. And I'll go ahead and also here, I'll also write a p minus 1, but that's the opposite of minus p plus 1, so I need to stick a little minus sign out in front here. Okay, and so now let's think about the case where p is a number bigger than 1. What happens then? Well, everything turns around the r to the p minus 1 part of the expression. What's happening to it? Well, since p is bigger than 1, p minus 1 is bigger than 0. And so r to the p minus 1 is r to a positive power. And we know that as r goes to infinity, that's got to go to infinity. So if that's going to infinity, then 1 over it right here has got to be going to 0. And so the result is that this entire expression will converge to 0, and you'll be left with just this in the limit. And so that gives you the part of the theorem that says that when p is bigger than 1, you get this for your limit, and you can write that as a to the 1 minus p if you like, instead of a to the minus p plus 1. Okay. In your future use of this theorem, it's not important so much what it converges to as just that the improper integral converges when p is bigger than 1. Now, what about if p is less than 1? Well, then r to the p minus 1 would be r to a negative power, okay? Like, think about the function x to the negative a half, 1 over the square root of x. That goes to 0 as x goes to infinity. So same way, r to a negative power has got to go to 0 as r goes to infinity. So that 1 over r to the p minus 1 in the expression up here, that's going to infinity. And so the result is that this expression here is also diverging. And so the whole expression up here diverges. There's no limit as r goes to infinity. You have infinite area underneath your curve. And so we get the part that the improper integral diverges when p is less than 1. Now, what about when p is equal to 1? Let's get back to that. Well, then your improper integral 1 over x to the p dx is just 1 over x dx. But wait a minute, we already found when we looked at the integral from 2 to infinity that this integral diverged. And so actually the same thing is going to happen for a to infinity, for any beginning positive value a. It really doesn't matter where you start. It only matters what's happening, with the r going off to infinity. If you redid the calculations with an a instead of a 2 in the example up here, just imagine you'll have, you'll have a's instead of 2's all the way through, and she'll be looking at a log of a here that has no effect on the fact that that whole expression goes to infinity. You'll see this with improper integrals all the time. It doesn't matter what real number you start at. On the left, it only matters, in terms of convergence, it only matters what's going on with the r going to infinity, as far as whether there's convergence or divergence. Okay, so let's get past the proof here. Yeah, and so just to, again, stressing, as far as convergence, divergence is concerned, where you start does not matter. If the integral converges, where you start will help to determine what the total area is, but it doesn't help to determine whether or not the integral converges. Okay, one more example before we leave this part of the chapter. Gabriel's horn. So consider the curve y equals 1 over x again, but this time let's start at 1 on the x-axis and just head out to infinity and look at the area underneath it, which we know would be infinite. But what I'm going to do is take that area and rotate it around the x-axis, getting a little solid of revolution, okay? And I wonder what the volume of that solid of revolution would be. It's kind of like this. You've got this this shape here, which is like a horn, because you can think of like this end here as the end of a trumpet, and then this like it's getting thinner and thinner and thinner, but infinitely far out. It's like an infinitely long horn, and the tip of the horn where you would blow with your mouth is infinitely far away. That's why they call it Gabriel's horn. You imagine this like angel infinitely far away blowing his horn, I guess. And you're wondering, like, suppose that you wanted to like fill the horn with like water. How many units of water would you, how many cubic units of water would you need in order to fill that horn all the way up? That's what this volume question is like. So if we analyze it with disks, just take vertical strips at some number x bigger than 1, so here would be a cross section of your disk. The radius is 1 over x. And we know the volume would be pi times the radius squared dx for the little thin cross section. Add them all up from 1 to infinity. This improper integral represents the volume. So let's give it a try. We know that that's going to be, by definition of improper integral, the integral from r to infinity of, the limit of as r goes to infinity of the integral from 1 to r. Now I'm going to pull the pi outside right away. It's constant. So I pull it all the way outside the limit sign. And I think about getting this antiderivative. So again, minus 1 over x, evaluate from 1 to r. Okay, and we have this expression here, which simplifies. This bit here just becomes 1. And we got 1 minus 1 over r. R is going to infinity, so this expression here is going to limit out to 1, and so we have pi times 1. Pi cubic units of water would fill Gabriel's horn, even though it's infinitely long. Okay, that's enough for this screencast. When we get back together, we'll talk about integrals that are improper on both ends. Bye-bye for now.